Okay, in this video lecture, I will go over a simple linear regression, something you have seen from the, I don't know, second year of undergrad. And here we will go inside of the linear algebra, the math of it. It's something that you all have seen, and it's an example which allows us to use everything we have learned, okay? And it's an entry for the rest of the lectures. And it's an example of a data modeling approach that I referred to when I was talking about the paper. What was that paper? Just for the sake of reference, I will bring it up here again. So the statistical modeling, the two cultures paper, and this lecture is an example of the data modeling culture. And it's the simplest example, so just so that you know what it is, we go over it. And the math will be useful for when we talk about, when we go beyond linear regression, okay? We will see that the math is actually the same, even if you have nonlinear regression, or if you have regularized regression, or if you have subset selection, the math is more or less the same. Okay, simple linear regression. Essentially, when we have a response, and we're talking about a regression problem, and we have a bunch of independent variables or features or predictors, xi can be a vector or can be a scalar, can just be one number. Then we assume that there is a relationship between the response and these predictors that's expressed to f. We don't know what f is. F is that nature which we like to estimate, and once we have it, it's good then, because tomorrow when we have a new data point x, we can make a prediction about it. Epsilon I is an irreducible error. We always assume it's the mean is 0. You may say, why is it 0? Because even if it's non-zero, if it's a constant, whatever it is, it can be absorbed into f. So this noise is always 0. Sometimes it's up, sometimes it's down. That's the whole point. There's no structure to it, but it has a variance which we call sigma square. Okay. Now, in simple linear regression, the assumption is that this function is a line, the simplest structure that we can have, a line. The relationship be expressed through a line. That's the simplest thing. We can do all the math, and this is what we're going to do here. So if fx is a line, then it has an intercept beta 0 and a slope beta 1, and then yi will be just beta 0 plus beta 1 xi plus epsilon I. Okay, and here xi is just one number, so we have one predictor. That's what we call. Okay, it's a simple linear regression. In matrix format, then we can create this vector y, which is n by 1, y1, y2 to yn. We have this matrix x, which has two columns. One column is filled with ones, and then the second column is just x1, x2, x3, xn. So it's n rows, two columns. And then we have a vector beta, which is beta 1 and beta 0. So why do we have this one? We have it so that we can express the intercept. Think about it. X beta, and then we have epsilon I, which is epsilon 1 to epsilon n. So now this relationship, which is true for all I that goes from 1 to n, can be expressed in matrix format as one line. Y is x beta plus epsilon. X is a matrix, beta is a vector, and epsilon is a vector. We assume that as we said, the mean of the noise, the irreducible error, is 0, and we always assume that the noises are independent. In other words, the variability for one observation doesn't have anything to do with the variability of another observation. The observations are independent. Okay. So when is that a realistic assumption? When we just gather, when we're talking about items, objects, individuals, this is typically correct. Okay, but if we are talking about time series, then this is not a correct assumption. The fluctuations of in today are dependent on the fluctuations yesterday. There is some dependence, okay? But this is, time series is not the subject of what we are considering here, so that's why we exclude it. But just so you know, in time series, it is a standard thing to assume that the variability between two time points which are near each other to have some sort of dependence. So independent noise, independent observation means that they're uncorrelated. That means that the covariance, which in this case is the expected value of epsilon I, epsilon j, because the expected value of epsilon 0 is 0 if I and j are different, and it is sigma square if I is equal to j. Okay? So that's our working assumption. What it means is that the covariance matrix of epsilon, which is expected value of epsilon, epsilon transpose, so epsilon is going to be a column vector, epsilon transpose is going to be a row vector, so epsilon, epsilon transpose will give you epsilon 1 square, epsilon 1, 2, epsilon 1 n, then you go down, epsilon here will be epsilon 1, epsilon 2, and then it comes down to epsilon 1, epsilon n, epsilon 2, epsilon n, epsilon n squared. Okay? Okay. Now, since we said that if I is not equal to j, the covariance term is 0, that means that the off-diagonal terms, these are the diagonal terms, it means that the off-diagonal terms are 0. So that means that the covariance matrix is a diagonal matrix, where the diagonal elements, the expected value of epsilon 1 square is just sigma square. Okay? So essentially, the expected value of epsilon times is sigma square I, where I, n by n, is the identity matrix. 1's on the diagonals, 0 on the off diagonals. Okay, so now what is y minus x beta, the L2 norm of it? Well, y minus x beta is itself a vector where the first entry is just y1 minus x1 transpose beta. Second entry is y2 minus x2 transpose beta. And the last entry is yn minus xn transpose beta. So the L2 norm of it is just, these are scalar. This is a scalar, this is a scalar, and this is a scalar. This is the first residual, second residual. But this transpose shouldn't be here. That's a mistake. Y is a scalar, so the yn, I mean, it's not a mistake, but it's just meaningless because y is a scalar, the transpose of a scalar is itself, so I just put it here by mistake. So there shouldn't be this transpose. And I need a 2 here too. There should be a 2. You know, this is an L2 norm squared, so there should be a 2 here. Okay, so let me just correct these while I am at it. So that in the notes, okay. Okay, it will, with some delay, it will show up in the screen. Anyway. So these are the residuals, and the L2 norm is just the sum of squares of the residuals, yi minus xi transpose beta. Okay, so here's something that's a little bit, might be confusing. what is this xi? This xi is different from that xi. So let me actually make this a little bit more different. I know how to do it. I added tilde. So okay. So xi tilde is a 2 by 1 matrix where the first entry is xi, the second entry is 1, and so xi tilde transpose beta is nothing but beta 1 xi plus beta 0. And just as a reminder, X is this n by p matrix where the first row is x1 tilde transpose, x2 tilde transpose, xn tilde transpose. Okay, so there will be a line here. It takes some time to update. Okay, here it is. Okay, so linear regression, when you run linear regression, essentially solves this optimization problem. Any statistical learning method solves an optimization problem, almost every, which it tries to find the best combination of coefficients that minimizes some risk, some sort of error. And here the error is the sum of the residual squares, which is the L2 norm. So we are trying to find the theta, a vector, such that it makes this quantity as small as possible. And whatever that theta is, we call it beta hat to indicate that this is an estimate of beta. So beta is the true unknown vector. We don't know about it. We assume it exists. And then we make some observations that are corrupted by noise, and then we use the data to estimate beta from the noisy data, and that estimate we call beta hat. Now, most of the optimization problems involving statistical learning methods do not have a closed form solution. There is no formula for it. You have to use numerical algorithms to find that best whatever theta parameters, okay? But for linear regression, Gaussian noise, the math just falls into place and we can easily calculate everything. Okay. So let's look at an example. If we have a convex function, what is a convex function? A convex function is a function that has this ball shape, like, okay, so it just goes down and then goes up. I mean, it's a little bit more than that. There is a condition which says that the second derivative has to be positive, but never mind that. Convex functions are lovely because they're smooth and they have a unique minimum, right? They have just one minimum, okay? So if we find a minimum, we know that's the minimum. If we found a minimum, we know it's the minimum, okay? And how do we find a minimum? Well, a local minimum is a point where the derivative of the function is 0, right? The derivative is the slope of the line that's tangent to the curve. Now, at the minimum, at the local minimum, You know why I say I local? Because we haven't looked at the function to the right and to the left. So in this area, this is a local minimum, and the derivative of the function at that point is 0. So the way we find these minimums is that we set this to 0, we find an equation, and then we solve it. Okay, that's why overdetermined and underdetermined equations that we talked about in the previous lectures are important. Sometimes this equation has many solutions, infinitely many solutions. Sometimes it has only one solution. Sometimes it doesn't have any solution. Okay, but in general, for models that are in the generalized linear model family, which means logistic regression, linear regression, Poisson, the corresponding function turns out to be convex. So if you find one minimum, that's the minimum, and that's why these models are so popular. Okay. Now, on the other hand, we can have functions that have multiple, or maybe even infinitely many minimums, local minimums. Here is a function. This is not convex, and has many local minimums. At all these local minimums, the derivative is 0. So if we write this equation will have many solutions. And if you find one solution, you will never know whether it's this one, whether it's the global minimum or it's just the local minimum. We can't look at the whole line of values, and that's something that can happen. It doesn't happen for the generalized linear model family, but it happens for very flexible models and neural networks that we'll see later. There are an example of kind of models where you will definitely end up in a local minimum. But because these networks are so flexible, even if you find the local minimum, or even if you're not at the local, you're close to the local minimum, it's so flexible that it's going to be good enough. So we don't really care if it's not the best minimum. And that's why initialization, having a good initial guess, matters a lot for neural networks. Because if you have an initial guess here, then you may end up here. If you have an initial guess here, then you will slide down here. So depending on what your initial guess is, you will slide down that valley. And that's why neural networks are also heavily sensitive to initialization. Okay, but this is not about neural networks. I just wanted to contrast it with simple linear regression. Okay, so where were we? The function that we're trying to minimize is the L2 norm of y minus x theta. So this function depends on many variables, not one. So what we had here was only a function of one variable. And that we already saw it's so complicated if we have many minimas. And if we have, at least if we had one minima, we could plot it and maybe see it. But if we have many variables, it's difficult. So what we need is for the gradient of this function to be 0, which means that the partial derivative of this function with respect to all the coordinates, all the coefficients, to be 0. So beta hat, the estimated coefficients, are such that the gradient of this function is 0 at that point. Now, what is the gradient of this? This is a little bit beyond of what is expected of you, but for the sake of completeness, I will go over it. But if it's a little bit, if you need to take your time here, that's normal, okay? For some of you, you won't need time. Some of you may need a little bit of time, but if you need to pause at this point and think about it or ask questions, that's all okay. Okay. So first thing is that y minus x transpose the L2 norm can be written as this. It can be expanded easily. How so? Essentially, this is y minus x theta so Okay, so y minus x theta L2 norm is just y minus x theta transpose y minus x theta. Well, you have y transpose y, you have y transpose negative x theta, you have x theta transpose y, you have x theta transpose x theta. And then this becomes y transpose y minus y transpose x theta minus theta transpose x transpose y, and so on. And then y transpose x theta is the same as theta transpose x transpose y. It's the same thing. Y, this is a scalar, and the transpose of a scalar itself. So essentially, y minus x transpose x theta L2 norm is y transpose y minus 2 y transpose x theta plus theta transpose x theta. Okay. So if you take the derivative, here you have a quadratic term. I mean, this going from this line to here takes a little bit of math, but just I'm skipping that. I mean, we can speak about this. Maybe if you have questions, I'm happy to explain it in the next lecture and make it clear. But essentially, here we have a quadratic term, and then this will end up to be 2x transpose x theta. Here we have a linear term because it only depends on theta, and if you take this off, you will end up with y transpose x. The row vector, so the column vector, will become x transpose y, and this is a constant with respect to theta, so derivative will be 0. So beta hat satisfies this equation, being equal to 0. So essentially, any beta hat that satisfies x transpose x, beta hat being x transpose y, is a minimum. Okay. So sometimes, if the number of observations is not large enough, actually if the number of predictors is larger than the number of observations, which is the underdetermined case, then you have many beta hats that satisfy that. But if n is greater than p, so you have more observation than the number of predictors, then and x is full rank, then this what will happen is this. You will see. Okay. So what does it mean for x to be full rank? It means that when n is greater than p, then x being full rank means that the columns are linearly independent. The columns of x. And if the columns of x are linearly independent, then x transpose x is invertible, and we can just multiply the inverse of x transpose x on both sides, so we have x transpose x inverse times x transpose y. And this is your beta hat. So when you run linear regression on any software, this is what the software does. It creates this x, calculates this matrix inverse, multiplies it by this observation. This is beta hat. Okay. So here's an example. In the first line, we just remove everything, erase the memory, clean everything, load the library, and we're working with the auto data. Okay, what is auto? Oh, you've seen it in the previous one. Okay, so auto is, again, let's look at it. Auto. Gas, mileage, horsepower, other information for 392 vehicles. Okay, and a summary of it shows the summary of each of the predictors. And these are the cars we have, like Ford Pinto, Toyota Corolla, AMC, and there are 365 of them. Okay. Now the response here for us is the first column, which is the mileage per gallon. And for the sake of simplicity, we want to predict the mileage per gallon as a function of horsepower. Okay, so here we take the fourth column, okay, which is horsepower, and place it in X. The length of Y will be the number of observations. Then we will create a matrix with n rows, 2 columns, fill it with 1s, but then the first column we fill it with X. So this capital X is like our capital X. The first column are the X's, the second column is just filled with 1s. And then we want to find beta hat. We just say solve this. So if A X is B, to find X, essentially in R we just write solve A and B. Okay, and this is X transpose X, this is X transpose Y, and if you go back to the notes, this is what we are doing. Okay, so this is our B, and X transpose X is our A. So this is beta hat. And then we can use that beta hat to get the Y hat, the estimates, estimated responses. And then we can estimate the noise variance. How do we do that? We look at the sum of the, this is Y minus Y hat, which is the residual, the transpose of the residual with itself. So it will be, this is the sum of the squares of the residuals. And then we divide this by n minus 2 to get an estimate of the noise variance. We make it numeric just so that R doesn't give us headache. And let's just leave this at here, at this point. There is more coming. Let's just stop here. Let's move here. Okay, so that's where we are. So let's just summarize what we have. If the true relationship is linear, so essentially we're saying, okay, this underlying relationship is linear, and we want to study how far what we estimate is from the true beta, which is unknown. This is how we would analyze it. We would say, okay, the true relationship is linear, so Y is X beta plus epsilon. Okay, so we place X beta plus epsilon here. So we have X transpose X inverse X transpose X beta plus epsilon. So we have this term multiplied by X beta, this term multiplied by epsilon. So we have X transpose X inverse X transpose X beta, X transpose X inverse X transpose X is identity. And so beta hat is beta plus X transpose X inverse X transpose epsilon. So if the relationship was truly linear, our estimate would be the true beta plus some corruption here, which is corrupted by this noise. Okay, and that's the error we get, and this is the irreducible error. Okay, well, this is, yes, with this amount of data, this is irreducible. Okay. But I mean, if we increase the data, so actually this is not irreducible, sorry. With more data, we can reduce this. The irreducible error is different. Okay, this is just an error. Okay, but the bottom line is that in the data modeling approach, we can all compute the risks that we're dealing with. We can say, okay, if the true relationship is linear and we just don't know what are the coefficients. If we have this much data, then this much will be the corruption. This will be the error. We don't know epsilon, but we know the epsilon variance, so we can say, okay, the size of this we can calculate, which will be the next thing. So this is all true if the assumption that the data is, so essentially if the data is generated by the linear model, okay, and if we further assume that the irreducible error between observations are independent, which we spoke before about, okay, then we can say that the expected value of beta hat is just beta. So beta hat is an unbiased estimate of beta. I mean, you can do the math. It's pretty straightforward going from here to here. But okay, again, as always, I suggest, so this is, I'm using the jumping from content, from notes to books. Sometimes the books are what are assigned reading, sometimes they are not, but this is available for free in the public domain. So bias what is the bias? Refers to the error that is introduced by approximating a real-life problem, which may be extremely complicated by a much simpler model. That's the bias. So here, that's not happening. The model is linear, and we use a linear model. Therefore, there is no bias, and the bias is 0. Okay, that's that. So this is what the linear model solves if 1 and 2 are satisfied, which means that the data is generated by linear model, the noises are independent, then expected value of beta hat. So an average or estimate gives us the same as the true, which is great. Also, what means that beta hat is an unbiased estimate of beta. Now let's look at the covariance of beta hat. The covariance of beta hat is the expected value of beta hat minus its expected value times beta hat minus its expected value transpose. But since the expected value of beta hat, which we just showed, is beta, so we can replace this with beta. On the other hand, beta hat is just beta plus x transpose x inverse x transpose epsilon. Okay. And the expected value of beta hat is beta. So if you subtract these two, you end up with x transpose x inverse x transpose epsilon transpose. I mean, this all looks tedious, but if you do it once, it becomes actually very clear. And I know this is, I mean, you may be watching this at the late night, or so it might not be landing immediately, especially if matrix algebra is your first time. But trust me, I had students who had no exposure, and they put the time, and they were curious, and they got it. So it's like a language, and once you get it, it becomes very easy, okay? But you should just, some diligence is needed, but once you apply it, then it will become clear. And the good thing is that we are doing this difficult math stuff at the beginning. I mean, if it's difficult, hopefully it's not, at the beginning of the semester, where you are still have more time as opposed towards the middle and end when you have other exams. Anyway, so beta hat minus the expected value of beta hat is x transpose x inverse times x transpose epsilon. Okay, so how do we compute this? Well, here we have a transpose, and the transpose of all these three elements will be the reverse of the transposes. So the epsilon transpose will come here, the transpose of x transpose will be x, and x transpose x inverse transpose is itself. Why is that the case? Why is that the case? X transpose X is a symmetric matrix, meaning that the transpose of it is X transpose X transpose transpose, which will be X transpose X. So you see the transpose of X transpose X is X transpose X. Therefore, it is symmetric. On the other hand, we know that the same way we can say that X transpose X inverse is symmetric. The inverse of a symmetric matrix is symmetric. So therefore, X transpose X inverse, and then transposing this is the self as X transpose X inverse. So this part is the yellow part is what gives us this here. Okay, this part. Anyway, so what we end up with is this long term, but you know, in the middle we have epsilon transpose, and the rest is x, and the x's are constant. They're not random. The only random thing here is epsilon, so we can take this out. So we have X transpose X inverse X transpose, and then we have the expected value of epsilon transpose, and then we have X transpose X times X transpose X inverse. Now this term here is sigma square identity. Look, earlier we talked about that. Makes things easy. So we have sigma square identity, and sigma square is a constant, is a scalar, and this is identity, so we can just take the sigma square out. Identity will give us X transpose X. X transpose X times its inverse gives us identity, so the covariance is just sigma square X transpose X inverse. This is how we find the covariance. And this is how confidence intervals and prediction intervals are calculated in linear regression. Everything that you saw comes from this math. This is the data modeling approach. Okay. So solve A is the matrix inverse of A. So in R, this is how we get the inverse. So this is X transpose X inverse, and then you have sigma 2 hat, an estimate of it. Okay. So now what can you do with this covariance matrix? Let's look at the for the simple linear regression model. Okay, X is X1, X11, X211, Xn1, right? And X transpose is X111, X211, Xn1. So X transpose X is this column, this row, inner product with this column, which gives us X1 square, X2 square to Xn square. This row inner product with this column gives us the sum of the xi's. This row inner product with this column gives us the sum of xi's. And then this row inner product with this column is just the sum of ones, n of them, gives us n. So X transpose X for the simple linear regression model boils down to this 2 by 2 matrix. Now here's some notation. Sum of xi square divided by n, we call it x2 bar. So sort of the sample mean of the x2, the square of the values. And then here we have the sample mean. Note that the sample mean of the squares is not the same as the square of the sample mean. Okay, it can be, but typically it's not. So x transpose x is just n times x2 bar times x bar 1. And since this is a 2 by 2 matrix, the inverse of it has a closed form solutions, closed form analytical formula, which you have seen before, I'm sure. Specifically, here it is. If we have a 2 by 2 matrix A, B, C, D, the inverse is just 1 divided by AD minus BC. You switch the A and D's and you make negative B and C. Okay. Now note that this inverse exists as long as AD minus BC is not 0. Because if AD minus BC is 0, then you have 1 over 0, which is undefined. Essentially, it's infinity. Okay, so now I want to speak about the interpretation of what it means for AD minus BC not to be 0. What does it mean for AD minus BC not to be 0? Okay. This is the bottom line. If AD is equal to BC, then the first column is essentially a rescaling of the second column. There is an alpha, where alpha is C over D, where if you multiply that by the second column, you get the first column. So what does it mean? That means that there's linear dependence, that the first column, there's some redundancy. The first column is pointing in the same direction as the second column. They're pointing in the same direction. Their length is different, but they're pointing in the same direction. There's redundancy. These two columns are linearly dependent. In other words, if AD is equal to BC, then this column and this column, they are linearly dependent, because we can add them or subtract them and get 0. Okay, so that's it. Now, likewise, we can show that if AD is not equal to BC, then the two columns are linearly independent. And since this is a 2 by 2 matrix, and it has two linearly independent columns, this matrix is full rank and it's invertible. Now, what is the inverse in this case? The covariance of beta, we said, is sigma square x transpose x inverse, right? So x transpose x is n times this. So the inverse of it is we switch the 1 and the x2 bar, and then we make negative here. And then the n becomes 1 over n. And then you have x2 bar times 1 minus x bar squared. Essentially, this is x transpose x inverse. And what do you want to do with it? You want to plug it in here times sigma squared to get the covariance of beta hat. In this case, the covariance of beta hat, this term will be the variance of beta 1 hat square. The off-diagonal terms will be the covariance between the intercept and the slope. And this diagonal term will be the variance of the intercept. Variance of the slope, variance of the intercept, covariance of intercept and slope. So essentially, the variance of the slope is just 1 over n times x2 bar, x bar squared times sigma squared, which is this one, right? Now, a little bit algebra can be helpful here. Note that the sum of xi minus its sample mean squared can be written as xi squared, x bar squared minus 2xi x bar. Okay, then you have the sum of xi squared. Then you have n x bar squared minus 2x bar sum of xi's. And the sum of xi's is what? Sum of xi divided by n is x bar. So the sum of xi is nothing but n x bar. And n x bar will give you 2n x bar squared. Here you have n x bar squared, and here, what is this? This is n times x2 bar. And then you subtract this, you get n x2 bar minus n x bar squared. So this quantity is the same as this quantity, which is here. So the variance of beta 1 hat is sigma square divided by the square root, divided by the sum of squares of xi minus x bar squared. Okay, so let's look at the page 66 of the ISLR book. 66. Okay, so these are formulas that you probably have seen before in introductory stat courses. Now you know where they're coming from. The standard error of beta 1 hat square is just sigma square over the sum xi minus x bar square. And that's what we had here. It's the same thing. Okay, but this is a data modeling approach. It starts with some assumption. Noise is independent, and the variance is the same sigma square, and the model is linear, and this is what we get. If we apply linear regression, it will be unbiased, but it will have some variability, and this variability depends on the noise variance, which is interesting. So the higher the noise variance, the higher our variability of our estimates. At the same time, here we have something that's the sum of squares, so this is always positive, and it depends on n. So the larger n, meaning the larger the sample size, the bigger this quantity, and the bigger this quantity, the smaller the variance. So here you have a trade-off. If the noise variance is large, the variance of our estimate will be large. On the other hand, we can reduce the variance of our estimate, the variability of our estimate, by having more data, which means making n larger. So n larger, more information, less uncertainty in our estimate. Okay, so it all makes sense. Similarly, if you do the same math, I won't do it. You can do it as a homework that you do not need to submit. You can calculate the variance of beta hat 0, and you will get this quantity. And this quantity again follows the same. I mean, even though it has this different form, it follows the same logic. The variance of the intercept depends on the noise variance. So the higher the noise variance, the higher the variability, uncertainty of our intercept. At the same time, if you increase the sample size, you have more information, this will become smaller, and this will become smaller. Because this quantity does not scale with n, it's an average. But this is a quantity which is the sum of n terms, all of them positive, and the larger the sample size, the bigger this. So again, here we have this trade-off, or not trade-off, but there are two forces active. One is the inherent irreducible variability. If the larger that is, the more uncertainty we have in our estimate. At the same time, we can reduce uncertainty by increasing information. And that's, again, what you have here. And this is the basis of confidence intervals, hypothesis testing, everything that we see in linear regression. And I wanted to express that in the linear algebra matrix notation because it will be useful later, and it will also give you a flavor of what it means to do a data modeling approach. Okay, now let's go to R and let's see. So in R, this is again, as we said, this is how we calculate the covariance, and then here we take the diagonal elements to get the variance terms. Remember the diagonal elements. The diagonal elements of the covariance are variance of beta 1. Sorry, this shouldn't be a square. When you have variance, there shouldn't be a square. Variance, let me just erase that. Okay. Takes always some time to update itself. Anyway, this square shouldn't be here. It's already a variance. This square shouldn't be here. But anyway, the diagonal elements of this covariance matrix, okay, now it's gone, are the variance terms. And so and then we take the square root to get the standard errors, okay? The standard errors. So I will just run it one by one. Okay, so the standard error of the slope is 0.006, and the standard error of the intercept is 0.717. Okay, now this is what we learned with our linear algebra approach. You know what's going on, and now we can imagine even for more complicated. Now in R, we can use the linear model function, which you essentially say, do a linear regression, regress y against x, and it gives you this object fit. You run it, and this fit has many things. Like the coefficients, residual, etc. Okay, but we don't want that. We just call the function summary, and the function summary gives us everything we want. It says that the R square is 0.6. So for regressing, the mileage per gallon against, so this is mpg, and this is horsepower, if I'm not mistaken. Okay. The intercept is 39. The standard error is 717, which is what we got here, and the standard error of the coefficient is 0.0664. Also, this beta hat is the same as what you would get from this function linear model. This is the same here, and this is the same here. Okay. So this was this is an illustrative example where you can just see R a little bit at work, matrix algebra at work, and you know where this is all coming. These standard errors and the t-values, you know these are all coming by on some assumptions. Okay, and then there's a math behind it, and you know now what's going on inside that box. So you can yourself now write this function, for example. I mean, you don't need to, but I'm just saying that you know what's going on inside this. Okay, now here we can plot the raw data. This is the raw data. I mean, later we will learn how to do better figures. This is pretty bad here because it doesn't have a title. We don't know really what y is, what x is, but I mean, we know y is mileage per gallon, x is horsepower, okay, and these are the data points, and it doesn't seem linear, but there is a decreasing relationship. And then here we can plot the line, the fitted line, okay, and this is the fitted line. All right, so I hope this was helpful to see a lot of things in the context of a simple linear regression problem. I know there was a lot of material, but I tried to go over a lot of things, and both R, math, statistics, real data, plotting, and linear algebra. So it was useful.